All right, so welcome back, students. So this particular tutorial is really the next segment in our lesson about electron theory. And what we're going to learn today is something called shortcut electron configurations. We're going to see that the periodic table takes on a shape that is definitely relevant or related to electron configuration. You notice on here that I have shaded 4 different colors: an orange, a green, kind of a pink, and kind of a very pale Carolina blue down here. So shortcut configuration, some skills that you would need to acquire, in order to understand them, is really what's coming in this lesson. So let us take a look at really, I guess, where the story begins. So one of the things that we know is that a periodic table takes on a shape, and the shape that it takes on has a lot to do with some of the things that we've already talked about. There being shapes that we would describe as simple sphere shape, shapes we would describe kind of as dumbbell shape, right? Shapes we would describe as kind of like clover shape, and then shapes that we would describe as sort of double clover shape. And that correlates to some things that we've talked about already. And I kind of want to make certain that we go back and take a look at that. So again, that S shape is kind of a sphere shape. Electrons could be located in orbitals of that shape. That P shape is sort of a dumbbell shape, right? And electrons, a pair of electrons, could be located in this particular orbital. D shape, right? Sort of a clover shape. F shape, a really complex thing, kind of a double-lobed clover. And those are the 4 shapes that electrons may occupy in what we know as orbitals. So we call those orbitals. And those shapes repeat themselves amongst energy levels. Okay, so what we're going to see then is we're going to see that at the bottom of the screen here, you see that the period number on a periodic table, there are numbers over here on the left. Those numbers reveal something about an electron configuration. What they reveal is they reveal what the last energy level is that you would put electrons in, or really the last orbital, I should probably say. So the period number reveals that 1, 2, 3, 4, 5, 6, 7. Then what we notice is that there are these different colors on here, and we're going to kind of highlight this so that you can sort of follow along. And any element that we see this orange color, if it lies in a region or in a square where this orange color is part of it, that element is a member of what we would call the S block, which really just means its electron configuration would end in the S orbitals. So S would be the last thing you write, either S1 or S2. Helium's also part of that. Right, the reason helium is over here is that that orbital is completely filled, and that kind of matches up with completely filled p orbitals. And later in this course, that'll become significant in something called octet rule. For today, not relevant. So what we notice then is we also notice that there is a region that we call P block, and that's shaded in purple here. And you're going to notice that P block is 6 elements wide. So it ranges from P1 position all the way to P6 position, P1, P2, P3, so on and so forth. So that's not a coincidence, folks. That's because in the P sublevel, you're permitted to place up to 6 electrons. So the last thing you would write for an element in this purple region would be something in a P orbital. Just like the last thing you would write for something in the orange positions would be something in an S orbital. So the next block we would call the D block. Anything in this green region here, the last thing you would write would end in the D block, or in D orbital. So an element located in this region on the periodic table is called a member of the D block. And then last but not least, at the very bottom of the table, right, we've got what's called the F block, and an element located in that region would be a member of what we call the F block. Now, what this allows us to do is it allows us to relate to something later in this lesson called shortcut configuration. So if we can sort of unlock the code about what would be the last thing we would write for an element, it would reveal a way to kind of check your work. Did I do the electron configuration correct? Kind of what I mean by that is if I look at this, right, this is the period number, period 2. Well, something that ends in 2s1, this is the only element that could end in 2s1 right here. Right here is the only element that could end in 2s2, right? They have unique electron configuration. If we move all the way over out of the s block into the p block, this would end at 2p1. Likewise, this would end at 2p6. If you jump down 1 period, now we show what ends at 3s1, what ends at 3s2, right? What ends at 3p1, right? What ends at 3p2, all the way up to 3p6. So we can kind of relate these to what element is represented by what we have written last in the filled orbital for any specific electron configuration. So let's relate that now to the actual periodic table. So here's a better version of really the periodic table itself, all completely filled in. So let's say we were interested in knowing what block sulfur was a member of. Well, we can chop the periodic table up into the blocks, right? We said the first block we looked at was kind of orange shaded, and that was this region right here. Right? And that also included helium, right? So this guy is not a member of the S block. The next one that we looked at was 6. Oops, it should include this one. My apologies. 6 elements wide. So that's called the P block. Sulfur is a member of the P block. It lands in a position where it ends with a p orbital as the last thing that has electrons. And as a matter of fact, sulfur would be in the 3p, 1, 2, 3, 4 position. 3p4 for sulfur, that would be the last thing you would write. You would write 3p4 as the last part of the configuration for sulfur. Okay, so again, we could highlight the other regions, right? Green was the region that we showed as being D block.
Good afternoon, everyone. Here are your
And then finally at the bottom of the periodic table here, this light blue region, we called that the F block. So we kind of have related it to the actual elements and their symbols on the periodic table. So let's see if we can't put into practice kind of what we're talking about here by using a number of examples. Okay, our first skill then, identify the electron block that an element belongs to. So we got the elements. Let's take tin and hydrogen first. So let's go back to our periodic table and let's highlight where tin is. Tin's located right here. Hydrogen, however, is located up here. What we notice then is tin is a member of what we call the P block. It's 6 elements wide, right? And it's actually in the P2 position, right? So tin is in P1, P2 position, right, in the P block. Hydrogen's in the S1 position, right, in the S block. So hydrogen, since hydrogen's in the S block, remember S only holds 2 electrons. So here's our S1 positions, any element down below it here, right? Here's our S2 positions, any element down below here. So we've answered the first portion of this. Tin is a member of what we would call the P block. Hydrogen, a member of what we would call the S block. Now we're going to do this again for neon and plutonium. Let's go back to our slide here. Plutonium down here on the bottom, right? Neon up here. Oh, well, neon's also in the P block in that region of purple shading where there are 6 elements across. Plutonium, however, is in the region where there's 14 elements across. So neon's in the P block, but plutonium found in the F block. Neon's in the P1, 2, 3, 4, 5, P6 position, right? Plutonium's in the F1, 2, 3, 4, F5 position. So we didn't really ask that yet, but neon we know is in the P block, plutonium in the F block. Okay, so that's the first skill that I wanted to make certain that we spoke about. How do we know what block an element is located in? Well, there are 4 regions in the periodic table. Now, I get that a normal periodic table doesn't have this fancy color coding, but we do notice it takes on about 4 shapes. The shapes would be very clear if helium, were placed over here where it really belongs. So we'll talk at another time about why it's actually there. Okay, so we have these 4 different shapes that form that relate directly to electron configuration. Next skill. Identify the element that ends with each orbital filling position on the periodic table. Now, in our notes, one of the things that I embedded is how we go about doing this. So how we go about doing this, it's stated here. So the period number is a number over here, like 7, 6. Those are period numbers. What they reveal is they reveal the energy level, the last thing that you would write for most electron configurations. They reveal what energy level. So for example, if we wrote 2s1, the energy level is 2. The period reveals that 2. If somebody wrote 3p4, right, that would be something in the 3rd period in the P4 position, P1, P2, P3, P4. That would be this element right here. So this is a way to kind of associate position in the periodic table to what is written in its electron configuration. So let's put that into practice. Now there is something that happens for the F block and the D block that's unique, and we'll come to that when we see an example for that. So 2p2, what element has energy level 2, p2 position electrons? So in the second energy level, p2 is the last thing we would write. So here's what we do. We go to a periodic table. We find, right, period 2. We jump over to the P block, P1, P2, right? Oh, that's the 3rd energy level, folks. So I should be looking at the 2nd, right? P1, P2. It's the element carbon. So 2p2, that's identifying the element carbon. That would be the last thing you would write for the configuration for carbon. Let's do it again for 4s2. Look at the energy level 4, but now in the S position, 2 in the S position. So 1, 2, that's this element right here. It's kind of buried there, right? It's calcium, right? So calcium would be in the 4s2 position. So let's put the symbols for it, Ca. We're going to skip this 3D and 5F. Let's take a look at one more example, and then we'll explain a little bit about some of the challenges with these two. So 3p6, right? We're going to find 3rd energy level 3, go over to P, right? In this row, 3rd energy level, this row, P1, P2, P3, P4, P5, P6. That's the element argon right here. So we will reveal that as being argon. Now, something we need to be careful of is what happens in the D block. Well, D block, and here's reasoning for it, something weird happens. After 3p, you would think that 3d would fill with electrons. Well, that's not the truth. Turns out the 4s orbitals are a little bit lower in energy than the 3d orbitals. So the 4s fills before the 3d. That makes this diagram in the periodic table off by 1 for any D block element. So even though the period here might say 4, for any D block element, that number's off by 1. that would actually be 3 for a D block element. So what we look for then is 3D6, right? 3D, we would find the number 4, subtract 1 from it because the D blocks are off by 1, and count over 6. 3D 1, 2, 3, 4, 5, 6. 3D6 would be the element iron. So iron is associated with the 3D6 position. Okay, I know that's a little confusing, but it all relates to what fills first, which orbitals are lower in energy. So something funky is going to happen again for the F block, except instead of it being off by 1, F block is off by 2. So the F block elements end in an energy level that is 2 less than the period indicated. Now, F block gets a little confusing because where it's located when you actually look at the periodic table, it's located in kind of a strange position. Okay, so let's take a look at what I mean by a strange position. 5F4. What we notice is that the F block squeezes into this region right here where that little black kind of line is, right? So if we just squish this up and jam it in there, that's where it goes. And then CE is in row 6 and TH is in row 7. Those numbers are actually off by 2. So we're trying to see what would end at 5F4. So actually this row right here would be 4. This row right here would be 5. So we'll count over to the 5F4 position. F1, F2, F3, F4. So neptunium, its configuration would actually end at 5F4, NP for neptunium. And that's how we relate the position on the periodic table to what its configuration would end with. And that's critical to really the next thing that I'd like you to begin to see. There's something called a shortcut electron configuration. And in order to understand the shortcuts, you kind of have to know where a configuration would end or be able to predict that. Okay, so that's a skill that I'll talk about here in just a moment. So what we're going to look at is this method. It's called a shortcut configuration. The reason it's called a shortcut is you do a little less writing to do one. So it's another method. It really displays the same info. It just looks odd, looks awkward if you've learned how to do them. In the normal method, they look a little weird in what we would call the shortcut method. So the shortcut method relates every element to what we call a noble gas. So what I mean by a noble gas would be on the periodic table, let's use a highlighter. Let's use a color we haven't used. Let's use this kind of pretty pink color. These are noble gases, all of these guys. So every shortcut configuration has a noble gas as part of it. So what we have to learn is, okay, so how do we figure out which noble gas to use? Well, that's really not that hard. So in brackets, one of these noble gases will appear in every shortcut configuration. So how do we make the choice which one to use? Well, let's take a look at our first example called sulfur. So sulfur, we want to locate it on the periodic table. And in the brackets, we're going to put symbols for a noble gas. So we're going to locate sulfur on the periodic table. Right, it's located right here. Let's clean that up a little bit. Sulfur is located right here. So what you're going to do then is you're going to go up into the row above it and go all the way over till you touch the noble gas. So that would be neon. What the shortcut says is the shortcut says that, hey, sulfur has all the same electrons as neon, except it has these unique parts. So we want to add the unique parts on to the neon that are in brackets. So let me show you again, and we'll come back and we'll demonstrate exactly how you get some of the rest of the detail for this. So we're going to put neon in brackets, Ne, and then what we're going to say is sulfur has all the same electrons as neon, which we need to latch in on. Neon has 10 electrons. If we look in the periodic table, atomic number 10. So we know that we already accounted for 10 of the electrons for sulfur, right? Neon has 10. What we're going to then add is, what are the unique parts that make this sulfur and not neon? Well, the unique part of it says we have to understand where neon ends. Neon is right here on the periodic table. So neon is in energy level 2, but in the P6 position, P1, P2, P3, P4, P5, P6. Neon ends at 2p6. So we know everything all the way up to 2p is completely filled. So we use that to our advantage to figure out what to do next. So if we go to the filling sequence, we know everything up to 2p is already filled. 1s is filled, 2s is filled, 2p is filled. What we would fill next is the next thing in sequence, 3s, until we use up all the electrons. So let's do that for this example till we use up all the electrons. So we know that neon used up 10 of them, right? And we know that we're going to begin to fill 3s after that because we've just determined that. So let's go and add to this, right? So we're going to add 3s. Because it's s, you're only allowed to add 2. So, and then after that, that's still only 12 electrons. And then 3p would fill after that. P could hold 6, but we're only going to use 4 because we ran out of electrons. And what I want you to realize is this usually is not part of it, this 10. It just lets you understand 10 plus 6 makes the 16 electrons we wanted, 10 plus 2 plus 4. So this is what we call the shortcut for sulfur. They always work the same way. So our next example is rubidium. Let's go to the periodic table, right? Let's find rubidium. Rubidium is this element right here. We said what you do is you go to the row above it and you go all the way over to the right till you touch the noble gases highlighted in pink, right? Krypton. Rubidium has all the same electrons as krypton, which in this case is 36, right? Rubidium has 37. So all the same electrons as krypton, except it has a unique part that identifies it as rubidium. So in this case, krypton is going to go in the brackets. So we put Kr in brackets, right? We keep track in our brain. 36 electrons are what krypton has. So it has all the same electrons as krypton. Everything is filled up until where krypton ends. So let's look at that. Where does krypton end? So we look at our periodic table to help us with that, right? Krypton is in this position, right? So let's get rid of some of this mess, right, from an irrelevant example. Let's put our shading back in for our noble gases. So what we're going to notice is that energy level 4 in the P block, P1, P2, P3, P4, P5, P6. Krypton ends at 4p6. So whatever fills after 4p6, that's where we start to add to the unique part, all the same electrons as krypton. So that means it's 1s is filled, 2s is filled, 2p is filled, 3s is filled, right? 3p is filled, right? We're trying to get to all the same electrons as krypton, right? So 4s is filled, 3d is filled, 4p is filled, right there, 4p6. The next thing that fills is 5s. So what we're going to do is we're going to add electrons till we get to the total for this element called rubidium. So 5s is the next thing that gets electrons, and we only need 37 to make rubidium. So we already had 36 that came from krypton, 5s1. It's called a shortcut, basically because you do less writing. Sometimes it's a little more thinking in the brain, but it means the same thing. All right, vanadium. Vanadium is an example where we're going to want to be careful because vanadium ends in what we would call the D block. So let's clean up our mess here a little bit. Okay, let's look at the periodic table. Let's find vanadium, clean up some of our mess. Okay, so vanadium, this element right here. We said you go up into the row above and then you go over till you find the noble gas. Now we're going to relate it to argon. Argon ends energy level 3, P6 location. So argon ends at 3P6. So everything up until 3P is filled, right? In fact, including 3P. So 1s is filled, 2s, 2P, 3s, 3P, all of that is full. The next thing that we're going to fill will be 4s, right? But we've got to keep track of total electrons, right? Argon already has 18, right? So we're going to make our brackets. And in our brackets for vanadium, we're going to say all the same electrons as argon. I'm just putting the number up here to keep track, 18, right? The numbers really are not part of it, but they help us keep track. So argon has 18. Now we add the unique parts. So whatever after 3P, right? After 3P, 4s fills, that's where we'll begin filling to add the unique parts, right? 4s, right? 4s can get up to 2. If we recall, vanadium needs 23 electrons. That's only 20. Well, what fills after 4s? We just filled this. Follow the sequence, 3D, right? But we need to use up the correct number of electrons. So 3D, we only need 23. So we're going to place the remaining 3 in that D block, or that D sublevel, I should say. So 3D3. Again, the number right here for argon's not really part of it, but it says all the same electrons as argon, plus these unique parts that make it vanadium. I hope that you can find use for this instructional tutorial if need be. So look it over maybe a couple times. If you're having some challenges with shortcut configuration, rewind back, look and see where we got sulfur and rubidiums from. But know that you have to have a periodic table handy, and you got to be intimately familiar with what this filling sequence diagram is really about. So until the next time, I ask you to try to respect your chemistry, but certainly don't fear it. I'll talk to you guys real soon. Have a great day.